Hello, everyone. It's a pleasure to introduce our speaker tonight, Professor Lloyd Knox, a leading astrophysicist from UC Davis. Professor Knox started his journey in physics at the University of Virginia and earned his PhD from the University of Chicago. Since 2001, he's been at UC Davis, making significant contributions in the field of cosmology, especially through his work on the WMAP and Planck observations. His work earned him a spot as a Fellow of the American Physical Society in 2012. Professor Knox isn't just about research. He's passionate about teaching and sharing his love of astronomy with people of all ages, from kids to astronomy enthusiasts like us. This week, he was appointed as the first Michael and Esther Vida Endowed Chair in Cosmology and Astrophysics at UC Davis, a big honor that celebrates his achievements and future contributions to the field. Tonight, he's going to talk about a fascinating topic, Cepheids, supernovae, and the cosmic microwave background. He'll explore the puzzle of why two ways of measuring how fast the universe is expanding give us different answers. Is it new physics at play, a need to tweak our current models, or just a simple error in measurement? His talk will surely give us a clearer view of the cosmic mystery and help us understand the science we often see in the media. Let's give a warm welcome to Professor Lloyd Knox.
All right, well, then let me step back and thank Awanish for that very generous introduction. I'm really glad to be able to be here to be with so many people who have enough curiosity about astronomy, curiosity like I do, enough curiosity that you're members of this society. And I'm kind of amazed that I've been here for 23 years, in Davis, and haven't been to your Astronomical Society yet. So I'm glad to finally be here and to learn something from the announcements beforehand about what you all are doing. Awanish really built up a lot of expectations. I'm not going to be able to meet them in an hour here. I'll do my best to share some of what's happening and that's of relevance to my research, and to share with you aspects that I find very beautiful about the universe we inhabit. So I am going to talk, as he said, about discrepant measures of the rate of expansion of the universe today. And but before getting into that, I'm going to step back to a story from the 19th century. So in the 19th century, well, in 1845, say, people knew about all the planets except for Neptune and Pluto, which anyway, they didn't know about these two solar system objects, Neptune and Pluto, but they knew about Uranus. And of course, in the 19th century, people had Newton's laws, and they could apply them to how Uranus should be moving. You could take Newton's laws, the known positions of the other planets, and actually calculate how Uranus should be moving. Of course, its motion is how it moves is dominated by the sun, but all the other planets are also pulling on Uranus and making some difference, particularly Jupiter. So a couple people worked out how Uranus should be moving and compared it to the way it actually is moving and found a discrepancy. So they both concluded that it's not moving in a manner consistent with Newton's laws and the known heavenly bodies. They both independently came up with solutions, which is like, well, there's another planet we haven't found yet. And they both figured out where this planet should be in the sky in order to be making Uranus move in the surprising way it's moving. By the way, I'm curious, how many of you actually know about this story? Okay, all right. So some, but not all. Okay. Now, John Couch Adams was a bit younger. He was in England. He had a hard time convincing anybody in England to actually point their telescope where he said they should to discover a planet. Urbain Le Verrier managed to convince Johann Galle to point his telescope in the right direction. And that very night, the first night aiming his telescope where Leverrier said to point it, he discovered Neptune. So that is a situation where there's that's a strong demonstration of the power of Newton's laws, right? So that you could find this discrepancy and say this could be explained by this extra planet. Go look for it, and you find it. It's a pretty strong statement about the explanatory power of Newtonian theory. By the way, let's go back and look at Adams here. He looks kind of like he's saying, look, next time I tell you where to point your telescope, just do it, okay? So, oops, sorry. So about 10 years later, Leverrier was sitting in a cafe in France. I'm sure he was smoking a cigarette, and he thought to himself, he had this troubling thought, oh, but what have I done lately? So he started thinking about the motion of Mercury and calculating, due to the influence of the other planets, how should Mercury be moving? And so planets move on ellipses. That's the main thing they do. If they were just influenced by the sun, we just said Newton's laws, they would move on ellipses, and that ellipse would stay in the same place. But due to the influences of the other planets, the motion gets changed from that somewhat. So it moves on an ellipse, but it's an ellipse that doesn't quite close on itself. So it's slowly rotating around the sky. So we call that the precession of the perihelion of Mercury, right? That point on the orbit of closest approach to the sun keeps changing. And it's easier to see how the point of farthest distance from the sun keeps changing, right? During the course of many, many orbits. And so he calculated using Newtonian theory what the rate of that precession should be. And he compared to the observations, and he came really close to getting what the observations imply. But there was a discrepancy of 1/10,000th of a degree per year. Now, he wasn't even using computers to do this, right? This is really impressive to do this. And certainly if I had done this calculation and got this level of agreement, I would have been very proud of myself and thought, yes, I got it right. He actually had enough confidence in the control of in the errors in the smallness of the errors in his calculation to conclude that this was a problem. So here's another planet not moving quite the way it should be according to Newton's laws and the other known planets. He actually tried the same solution to this. He proposed the planet Vulcan, which we know today as just a fictional planet. So that was not the right answer. But there was this conflict, and that's what I want to bring up as an analogy to the situation we have today with the rate of expansion of space. And so I want to spell it out like this. So we have two different ways of getting at what the rate of perihelion precession of Mercury is. We have a less model-dependent way, which is to observe Mercury's position in the sky over time and figure it out from that. So it's a much more direct approach. And then there's a more model-dependent way, which is to take a very successful theory plus solar system observations, right, and predict the rate that Mercury should be precessing as it's influenced by all these planets that we've observed here. And we come to different rates. This is an exciting analogy from what I'm talking about, because the conclusion of this is tremendously exciting. This could be a whole other talk. This motion was not, this discrepancy was not figured out until Einstein figured it out in 1915. He wasn't trying to figure out, but it emerged as a consequence of his general theory of relativity. And in 1915, before he published, he realized that he had the answer to this long-standing problem of the motion of Mercury. It really boosted his confidence that he was on the right track. So that's a whole other story. What I'm trying to set up now is this conflict that was there. And this is the situation we may be in now with the rate of expansion of space. So just as far as setting that up, I want to pause here to see if on this content any questions or that might help to clarify anything that I've said so far. Yes.
That 1/10,000th of a degree discrepancy, in modern statistics, would that be like only a 2 sigma degree of confidence versus, you know, like out there 5 sigma for the really confident stuff? I mean, just venture
Yeah,
a guess.
I have, people react, you know, so I'm not a professional historian. But from what I know, the little I know of the history, people did take this very seriously. And I have not seen any characterization of the statistical significance. That's a good, I'd kind of like to know. I like your question. I don't know. I think it was more than a 2 sigma discrepancy, though, given the amount of attention it did get, actually.
Okay, all right.
Yes.
On the previous slide, comparing the one before that, there we go. What is the difference between, in the left-hand column at the bottom, measurement of the actual rate of the perihelion precession versus the middle of the right-hand column where you're
Oh,
taking
yeah,
the actual
thanks.
sources?
So this, I mean, observations of all the other planets besides Mercury. Right.
Does it include Mercury or?
Well, I guess it includes Mercury too, so that you know, but you can assume that Mercury is on an elliptical orbit. And and observe where everything else is, you know, the forces that are impacting it as it goes around that orbit, and figure out how it's going to be precessing. Yeah, okay, thanks for those questions. So let's go on. So this figure, I promise it will get a little more interesting than this. Right now, it hardly seems like, why would I give anybody credit for this figure? But let me start here. There'll be more on it. So this is how we quantify the rate of expansion of space, which is in these units of kilometers per second per megaparsec. And that's because you can think of the expansion of space as actually a creation of space that's happening over time uniformly through the cosmos. And so this is saying, you know, if we have an expansion rate of say 70 kilometers per second per megaparsec, that's stating that in every megaparsec of space, there's 70 new kilometers created every second. And this discrepancy that we'll venture into is that if we take a more direct method, really it's less model dependent approach to inferring the expansion rate, we get an answer up at 73. And then if we take this much more model dependent approach of taking this highly successful model, in this case our standard cosmological model, and constrain it with other data, constrain the parameters of that model with other data, we can then predict what the expansion rate should be today, and we get this discrepancy. And what's exciting about it is that this discrepancy may be because our standard cosmological model is wrong. That was the case with the analogy I just told you about, where the solution was that Newton's gravitational theory was actually incorrect. Right? It's this excellent approximation, and but Einstein's theory is a deeper theory and more correct theory. So this is what I'm going to run through. I'm going to talk some more about the expansion of space. It's in some ways that the universe is expanding, and what that means is a much more exciting thing that there's this small discrepancy in the ways we infer the rate of that expansion. So I want to talk about that. And then I'll talk about measuring it directly with Cepheids and supernovae, and we'll say something about using this standard cosmological model and observations of the cosmic microwave background to get at that rate in a different way. So let's talk about the expansion of space, and this is something that we really understand thanks to Einstein's theory. So let me start off with the single most popular equation in the world. This was Einstein's 1905 platinum hit, E equals mc squared. Everybody knows this equation. 1915, he came out with this. Somehow it just didn't catch on as much. And I just, this is something that, of course, takes years of study to begin to understand what these symbols even mean. But I just have this up here just to tell you that, the theory is one of space and time and how matter influences space and time. The things over here describe properties of space. And this describes the mass and energy distribution. And the takeaway from this slide is just that matter affects properties of space, which then leads to the question, what are you talking about properties of space? Space is space. It's just this thing through which things happen. How do you have properties of space? And so let me give you an example, property of space. This is something, we expect if we lay out a set of points that are all, if we lay out a set of points that are all equidistant from a central point, we have a circle. And if the distance from the center to the circle is r, then the circumference we expect to be 2 pi r. And if there's no mass present, that's in fact, what happens. But if there's some mass at the center, it actually distorts the space away from these Euclidean properties that we learned about in school. I have to reject this phone call. And so with this mass at the center, it actually reduces the circumference so that it's less than 2 pi r. So I see a pained expression on your face there in the front row, which means that you're absorbing some of this. If you were like, oh yeah, of course, then I'd be worried. So this is really strange. And this is a small effect. So the correction to the circumference of the moon's orbit is just about 10 centimeters due to the presence of the mass of the Earth. That's why we don't notice it in our daily lives. Not to mention the fact that in your daily lives, you don't measure circumferences of circles that often, but even if you did, you wouldn't notice this. So I want to, and now these, I skipped somewhere in my slides. Somehow I went backwards. And I'll have to get back to, okay. So to help you visualize a space that's that's distorted, like that circumference being small, I'm enlisting the imaginative powers of the creators of Doctor Who. And so here's before going to questions and discussion about this, let me just say that, let me just connect this now with the expansion of space. What I want you to do is to be able to imagine, that I have a box here, you have a box right in front of you, and you open it up and you see a really unusually large amount of space. Okay, you were just helped in that imagining by this video, right? And now close it, open it up again, and it's even bigger. The box hasn't changed in size outside, right? The exterior of the box is the same. You open it up, it's even bigger. That's like the expansion of space. So there's new space being created over time in the box. And it's genuinely new space, right? It's not just that we're making the box bigger so it's moving out and occupying more previously existing space. There's new space being created. So now let's pause for any questions or discussion.
So what you're saying is, it isn't that the universe is expanding into anything.
Right.
Space is being created as needed, or at 67 kilometers per second per megaparsec. And that's what it's expanding at the same rate that we're expanding. Space is being created at that rate.
That's right. That's right. Yeah. Sure. Yeah.
But in our space, what's creating the box? What's the boundary? I've always.
Oh, right.
That it just expanding.
Yeah. So, right. So that's the next step in the imagining process, is to now imagine the box getting really, really, really big, and that you're inside here, and the walls of that box get so far away they're not even part of the, you're not even aware of them, and they don't even exist, right? So, yeah. So the analogy breaks down that we're not, as far as certainly as far as we've probed in the observable universe, we're not inside a box, right? As far as we know, this space is going on forever, right? You know, the universe may be finite, but if it is, the volume is much larger than what we can, than the observable universe. Yeah.
So in high school decades ago, people talk about distant objects receding at increasing velocities.
Yes.
But this is exactly the same as what you're describing, only a different way of thinking about it.
Absolutely.
Objects are not really, well, they're in relative motion, I guess, with respect to us. But it's not a property of those objects. It's, as you say, new space.
Exactly. Thank you. So yes, the objects are getting further and further away from us, and that's because of that new space being created in between us and them. Yeah.
My question is about the new space. It appears there. It doesn't appear to be tachyon resistant. Gamma rays go through it. Everything seems to pass through this new space, however you define it. What can you say as an astrophysics defines some cubic volume or some measure of the new space? Is there anything that defines it from the old space?
No.
Okay, so we're making a basic assumption that expansion in the universe and the space appears. We don't have a lot of supporting data.
No. I'm realizing with your question that it's kind of implicit in what I'm saying is that there's some distinction between old space and new space. And I'm saying there isn't. You know, maybe this new space is maybe thinking about it more like, you know, some stretching of the existing space. You know, so it's not like we can distinguish. Oh, here's the old and here's the new. That's not part of the theory. And this theoretical model is extraordinarily successful. So there's all kinds of data to back up. If you know, the words I'm talking about, using to talk about this, like we're creating new space, these are just words. But if you take the theory and you manage to predict what you should observe, Einstein's theory is just extraordinarily successful in so many different domains, right? Including, you know, starting in 2016 with what happens when, you know, 30 solar mass black holes spin into each other and send out gravitational waves. So there's all kinds of data backing up this picture that I'm presenting. Yeah, thanks.
Can you say a word about how this would compare with Doppler shift from these preceding objects?
Right. So yes. So one of the effects of the expansion, one of the important effects of the expansion, this increasing distance from us to other objects over time is a redshift. And another source of redshift is, well, maybe the object is actually moving through space, right? And there's a Doppler effect. And those can combine. Importantly, those can be confusing. You know, we don't know, is this from expansion or is this from because the object is actually moving with respect to cosmic rest? And in fact, it's a reason, in order to measure the expansion of the universe, because of this, we have to get out to distances where the expansion is a big contribution to the observed redshift.
Much larger than possible velocity.
Right. Okay, thank you for all that interaction. And let's continue on to measuring it directly with Cepheids and supernovae, and I'll be saying more about redshift here. So this expansion rate is determined in this direct cosmological model independent way by measuring distances and redshifts. So what are redshifts that we've just been talking about? I'm sure many of you already know what redshifts are, but this is the definition. It's just the wavelength of the light observed divided by the wavelength of the light emitted. And this quantity z, we just give the name redshift. And we'll get to distances later and how you combine distances with redshifts to get to the expansion rate. But let's just look at redshifts for the moment. And I think this is stuff many of you know, but it's still kind of neat to look at these results from the James Webb Space Telescope. And particularly in this context of, well, in this context, I'll give you for cosmological expansion as the origin of the redshifts rather than a Doppler effect. So on the top panel is this image from the James Webb Space Telescope. And there's a zoom in to this light from this galaxy that is so far away that the light left that galaxy 13.1 billion years ago. At least so we think, assuming cosmological models. The people using the James Webb Space Telescope can also take a spectrum of that object, right? Break up the light into its different wavelengths, measure the intensity of the light there on the x-axis relative to the wavelength of the light, intensity on the y-axis relative to the wavelength on the x-axis. And we'll zoom in on that some because this is impossible to see. And so, and one can see emission lines in the spectrum of this galaxy. And knowing what we know about atomic physics, managed to find the patterns in these emission lines and determine what elements and even what electronic transitions in what elements created the light at each of these lines. And for reference down here, here's a hydrogen emission line spectrum where labeled with their common names, H alpha, H beta. There's a very difficult to see blue one there, H gamma. And these are the rest frame wavelengths. For example, this H beta here is 486 over to H beta on the light blue. Somebody's moving a cursor over
Me.
can you move it over to H beta?
Oh, it's right here. This is
No, H beta, there's one more, yeah.
H beta's right here, but
Yeah.
the blue line was over there.
Okay, thanks. So H beta is 486.1 nanometers. And the people analyzing the spectrum claim that that line over there on the top is H beta, and that's at a wavelength of 4,610 nanometers. So we take that ratio, right, and we get 9.49. And so what was the rest frame? What was this emission from hydrogen 13.1 billion years ago at presumably at 486 nanometers has been stretched out by the expansion of space to 4,610 nanometers. And apparently the universe has expanded by a factor of 9.5 since that time. And that's what leads to this stretching of the wavelength of the light. Yeah. Why are there three different lines? If you actually take a hydrogen gas and send electrons through it to ionize. Oh, right. Why are there so many different things? These are different transitions in hydrogen. And I'm only labeling right now. So far, I've only labeled a couple of them what they are. But this is just the spectrum of hydrogen. And if we look at H gamma, it works out the same way, right? The rest frame is 434 nanometers. The observed wavelength is 4,120 nanometers. And again, that ratio is basically 9.5. So remember, it's one plus z. That's the ratio of observed wavelength to emitted wavelength. And so if 1 plus z is 9.5, the redshift is 8.5. Okay, let me pause here. Again, we had a couple questions during that. Maybe I can go on.
So is that consistent with models right now, or is it detecting things that are making us question the model? Because
Yeah, that's a big question right now. So Amanish's question was, I think was suggesting this. Let me put a little into your question, which I think is the origin of it, which is that there are more galaxies being discovered at these very high redshifts, these great distances, than were expected in most models of galaxy formation. So this is a surprise that the community is wrestling with, but is
right. So you're saying now they're learning that galaxies were probably created much sooner than expected based on the current models.
Right, right. And yeah, yes, but that is not the discrepancy I'm here to talk about today. All right. And I guess I've already answered this question, but let me give it again. So what happened? Why did the wavelengths increase, right, over these 13.1 billion years? And it's part of this expansion of space as I've been describing it, right? So as that light was, one way of imagining the expansion of space is taking our 3D universe and reducing it to 2 dimensions on the surface of a ball, right? So this spherical model of a universe, and just imagining that ball to be expanding, and as the light is traveling from one object to another, if a lot of expansion has taken place in that time, that stretching of space is also stretching out the wavelengths of light, leading to that redshift, and we can conclude that actually the universe has expanded by a factor of 9.5 since light left this object, based on that ratio of wavelengths being 9.5.
Is that a number without any things next to it, or just a straightforward number?
I like your interest in uncertainties and characterizing uncertainties. And I am sure that there is a reported error on that redshift. And I also know it would be very, very small. And it just wasn't important for our discussion here. Yeah. To me, if you measure something and you don't report an uncertainty, you haven't measured anything. Right? It's an important part. So I appreciate the point. How do we actually get to the expansion rate? Well, at least for low redshifts, we have this simple relationship between redshift and distance that brings in the Hubble constant as well as the speed of light. And let me at least give some qualitative motivation for this. Why would something further away lead to a larger redshift? Well, if it's further away, it has to travel for longer to get here. So the universe undergoes more expansion in that time. So that's why higher redshift is related to larger distance. And of course, if the universe is expanding more rapidly, then that would also lead to, for a given distance, if the universe is expanding more rapidly, so h naught's higher, then that will also boost up the redshift. So this relationship at least should make some intuitive sense. And if we can, it also tells us that if we can measure redshift and distance, then we can, and we know the speed of light, then we can infer the rate of expansion. So that brings up the question of how we determine distances. And one can do this. One has to do this in several steps because we need to get out to distances that are far enough away that the effect of expansion is large enough. So, I mean, going back to this equation, there's other things that can lead to a redshift, right? Like a Doppler effect. And we want to be in a regime where this is the dominant source of the redshift, and where we can get there if we go out to far enough distances. We can measure distances geometrically to Cepheid stars in our own galaxy using parallax. And I'm assuming that in this Astronomical Society, let's see, maybe I shouldn't assume it. When I teach an introduction to cosmology to our physics majors, the one lab we do is in this theoretical course is I take them all outside and find a distant object, and they all hold out their thumbs and blink back and forth, and they can see their thumbs moving with respect to the distant object, and then they measure the distance between their eyes, and then from the angular side extent of the shift, they determine how far away their thumbs are, how long their arms are. One One year I had the width of the thumb wrong. The first did this, and everybody in the class ended up with these gorilla, like 2-meter long arms. Yeah, most recently, everybody was out in the breezeway doing this, and this group walked by and went. Anyway, that's the phenomenon of parallax. And as the Earth goes around the sun, the sufficiently nearby stars have a significant parallax effect. You can see that they move with respect to the background stars, just like the position of your thumb does as you move from one eye to the other. So that's parallax. We can determine a distance to these bright and wonderfully regular variable stars called Cepheids. And let me zoom in on this. So we can do parallax now out to quite a large distance, far enough away that lots of Cepheids can be measured. And the reasons that's interesting is because of a phenomenon discovered by Henrietta Leavitt over 100 years ago, that Cepheid variable stars have this relationship between their period of variability and their luminosity. So we can measure their period, and if we know how far away they are, then we can calibrate this relationship between period and we can measure how bright they are. We can measure their periods, and if we know the distance, then we can determine, well, how luminous do they have to be in order to be seen as that bright. We can start using these things then as standard candles. Right? Measure the period. You know how luminous it is from having calibrated them with parallax. You know how luminous they are. And so now you can see Cepheids that are even further away, measure their period, see how bright they are, and from that infer their distance. Right? The further away they are, the dimmer they'll be. And you can use that to determine the distance. So that gets us out further than we can get with parallax. Gets us out to nearby galaxies, and that's what's schematically put here on the side here. So these galaxies are quite a ways, out of our galaxy, but they're nearby galaxies, and they host both Cepheids and type 1a supernovae. So now we can use Cepheids in the same galaxies as type 1a supernovae to calibrate type 1a supernovae, these incredibly luminous explosions. And the supernovae are fairly regular. And we can use them to go out even further than we can see Cepheids. So Cepheids are just stars. They're particularly bright stars, but we can't see them beyond these nearest galaxies. But supernovae we can see to very large distances. And so we can observe supernovae because they're calibrated. We can turn their brightness into a distance measure, and we can easily measure their redshifts. And so we can make a graph like this, where this is distance to supernova on the y-axis and speed of light times redshift on the x-axis. Here I'm finally showing some data with uncertainties. Right, those are the small points with error bars on them. Although I don't have any uncertainty in the redshift. And there's 3 different slopes put here. Remember, it was CZ equals H naught times D. So H naught controls the slope of this line. There's H naught equals 150 is the red line. H naught equals 50 is the orange line. And H naught equals 70 gives a, by eye, just gives a decent fit to this line, indicating that there's around 70 kilometers of space created in every megaparsec every second. So that is very quickly an explanation of where this 73 plus or minus 1 comes from. Of course, there's a lot of important details in that that have been glossed over. And this is another point where I should pause for questions. Let's see. Sure.
So
How does dark matter enter into this? Does it affect this cosmological constant, or is it known if it affects it?
Absolutely, absolutely, it's highly related. Let me maybe ask that again at the end. Right now I'm looking for stuff that would clarify what we're talking about already. Yeah.
So the qualification for all of what you said in terms of this almost 70 number, is that in a, well, really where I'm going with trying to understand this. So I somehow want to think space is flat, not a sphere.
Right.
And so have we qualified that? Do we know the space is a sphere, or do we know it's flat, or neither do we know?
Yeah, so our measurements of what we call the mean curvature of space, which is what you're getting at, where 0 would be flat, which means Euclidean, right? Euclidean geometry, at least on the average across the universe. Our measurement of that average curvature is consistent with 0. So you're getting the universe is giving you what you said you want. So in this sphere model, right? That means that if it is a sphere, it's so big that we're only probing a tiny fraction, a tiny little amount of it, where it's a small enough region that it looks consistent with flat. And let me hold off just to make sure we get through a little more, because I want to say a little bit now. I'm not going to be able to explain to you how we use observations of the cosmic microwave background to determine the expansion rate. There's just way too much we'd have to go through. But I want to at least tell you what the cosmic microwave background is and something about that. So we know the universe today is filled with the thermal bath of radiation of photons with a temperature of about 3 degrees Kelvin. And it's cooling as it expands, so it was hotter in the past. So all with the expansion, not only does light get stretched out, but all particles motion slow down due to the expansion. So particles that were moving rapidly in the past, that's heat. As the universe expands, that cools. Here's this cartoon thermal history of the universe. I'm sorry, there's so much information on here that you do not need to look at the cartoon. Don't try to read all the words. Actually, here, I've got a slide where it's clean, or at least some of that's cleaned up to be less distracting. So this is this cartoon thermal history of the universe. The universe used to be so hot that it was the gas of hydrogen and helium that filled the universe was ionized, right? If an atom formed temporarily, some high energy light particle would come along and blast it apart. So the universe was ionized, separated into nuclei and electrons, and particles of light readily scatter off of free electrons, just like in the sun. And so the universe was this opaque plasma. Light couldn't travel through it freely until, with enough expansion, it cooled enough at around 500,000 years, it transitioned to a neutral gas. So it cooled enough, a temperature of around 3,000 degrees Kelvin, it became a neutral gas rather than this ionized plasma. And this thermal light that filled the universe could start streaming freely across it. So the universe is highly homogeneous. Let's think of a map of the universe with us in the middle. And in this map, we're also, as we go away from us, we're also going back in time on what we call our past light cone. So as we're going away from us, we're going back in time, just like the sun, right? The sun is, it takes light 8 minutes to get from the sun. So we're seeing the sun as it was 8 minutes ago. And on this diagram, same way, right? As you go further away from us, you're going back in time. All the way to the time of this transition. So the universe is nearly homogeneous. This transition happened about everywhere all at once. So it happened everywhere, but where everywhere that it happened, light started flowing everywhere. And on the boundary that says 2,970 Kelvin, that's where that light that left there at the time of that transition is just getting here today. Right? So all of this transition happened everywhere. Where it happened further away, that light hasn't gotten to us yet. Where it happened closer by, that light got to us a long time ago and kept going. Or it got absorbed. So we can actually image this light today and basically get an image of this huge surface so far away from us that this light has been traveling for almost 14 billion years and just got here today. What does this look like? Well, here's just to orient you, here's the optical sky at night. And if your eyes were sensitive to wavelengths 2,000 times longer, microwave wavelengths, then you'd see something like this, where the color here indicates brightness of light. And that doesn't look too interesting. But that reflects how uniform the universe was at those times. It used to be highly homogeneous. And if we subtract off the mean, though, it starts to look a bit more interesting. And we have this here with a different color scale. I like this image. This is what the sky would look like. Again, if your eyes had were sensitive to wavelengths 2,000 times longer, and you could really see the sky with very high contrast. Now, that's the beautiful thing, the beautiful data we can use to actually manage to determine the Hubble constant together with our standard cosmological model. And I want to return now to our analogy with the solar system, right? We've got these two wonderful gifts of nature, the solar system and the primordial plasma. Beautiful in this sense. Usually nature is so complicated, we can't calculate what's going to happen from first principles. We can't figure it out. It's too complicated. That's why we design experiments. We create artificially simple conditions where we can actually calculate what should happen, and then we can test those calculations, right? But here we're doing observational work. There are two gifts of nature. Well, there's more, but these are the two I'm talking about that are just real beautiful gifts to those interested in discovering the laws of nature. So we've already talked about the solar system, this unusually simple and regular natural system. We saw it at play in the beginning, right? You can make observations, you can do calculations, you can compare them. There's a lot to compare. There's a whole bunch of different planets. They move at different rates, right? There's retrograde motion. It's an interesting system. You know, you can get a lot of numbers out of it. It's not just it's rich. You can learn a lot from it. Highly successful theory as we talked about. The primordial plasma that I just talked about, that we can image at the time it started to disappear. We can make this image of the primordial plasma in this sphere around us, really far away. And that plasma is an unusually simple natural system where we can take a model, calculate things. We can actually manage to observe it. Of course, it took a long time to be able to do that. It's not as easy to observe as planets. And it is also phenomenologically rich. And we have this highly successful theory that I'm sorry I didn't get to tell you more about, this lambda CDM model. So why do we get these different results, right, from this cosmological model dependent approach and the model independent approach? I don't know. I'd really like to know what's possibly going on. Well, we do have this funny situation. Somebody mentioned dark matter. We need, you know, for in our standard model, in order for it to explain the things it does, we also need another dark component that isn't in the particle physics standard model, right? We have no evidence for dark matter and dark energy from laboratory experiments on Earth. We really need them to understand the cosmos. That's the breakdown today. At this time of this transition, it was very different. And one possible solution is that we're seeing the influence. One possible reason we're getting the Hubble constant wrong today is we're seeing the influence of an additional dark component at early times. It's just, you know, there's many different varieties of what this of theories out there about what this component could be. Well, we're really not sure if that's the answer or not yet. So I've been talking for a long time. I should stop. So new space is being created continually, right? That's the concept of the expansion of space is a pretty mind-blowing one. So thank you for allowing me to talk about it some. This primordial plasma, like the solar system, is another great gift of nature to those of us trying to understand it. The system is simple enough that we can actually make calculations and compare with observations. I didn't have time to tell you about all the successes of the standard cosmological model that I've seen unfold over the course of my career. There's one significant discrepancy. This predicted expansion rate today differs from the most precise measurements, most precise direct measurements of the Hubble constant, and we don't know why. So thank you all for your attention.